Hello everyone, this is Dr. Krishnasree, Associate Professor from Department of ECE. Today I would like to explain about the linear integrated circuits, and one special IC in linear integrated circuit and very popular IC is IC555 timer. As the name indicates, this timer is going to give us lot of applications like burglar alarms, toxic alarms, electronic eyes, voltage regulators, function generators, and many more applications we can build by using this timer IC. So that's why it is very popular and very simple circuit, simple integrated circuit, which comes under the linear integrated circuits. So the timer, as the name indicates, there is a timing component known as capacitor, which does the timing operation, that is how much time we can either create or we can wait or we can modify. So all this is depending on one basic component known as capacitor. And along with the capacitor, we have to use few resistor components so that we can build up a lot of applications based on this 555 timer. So today what I am going to discuss about is how this integrated circuit is designed internally and how many modes it can operate, and each mode how it is useful. In brief, I would like to explain. 555 timer is a 8-pin dual inline package, that is it contains 8 pins on 2 sides. So that's why it is known as dual inline package. So it is capable of producing accurate time delays or oscillations, as I told, and it is produced by Signetics company in the year 1972. So it is still widespread used to generate clock pulses or square or rectangular waveforms even today. A single 555 timer can provide the time delay ranging from microseconds to hours. So basically it operates on a simple power supply from 5 volts to 18 volts. Normally we can use the minimum voltage for any kind of applications. If you look at the internal schematic diagram, it contains few components. There are two very simple components, like one simple potential divider circuit which provides us the threshold voltages for 2 comparators which are available inside, which are known as upper comparator, also a threshold comparator, and lower comparator, also a trigger comparator. The outputs of these comparators are provided to SR flip-flop, which is also very simple basic flip-flop, and the output is driven through an inverter. This purpose of this inverter is to provide more current capability when you want to drive some heavier loads. And two transistors are available inside. One transistor is the transistor which is available on the lower side. So that is meant for, so this lower transistor, what I am producing or what I am rounding is meant for charging and discharging signaling path for capacitor, and the upper transistor, it is meant for the resetting the complete IC whenever you want to reset to 0 voltage. So these two signals, these two transistors are meant for, one is for resetting the IC, another is maintaining the capacitor to charge or to allow the capacitor to charge or discharge. Now as you see, it has some numberings. You can see like this, number 2, number 3, number 4, number 5. So all these numbers are internally, there is a schematic diagram, there is a circuit diagram, but from the outside, to make the connections and make it operative, we have to take these pins outside, and each pin will have its own significance. Let us see the physically really how it looks like. So here the as name indicates, it is NE555 timer. The first 2 letters NE indicates the company it is making. The next 3 letters indicates the number of IC, and the last one indicates the temperature range. So it can operate in different temperatures, so that it is useful for either commercial purpose or military purpose. Now let us see how many pins are available, and if you look at the pin diagram of 555, the 0 here indicates the starting pin number. like 1, 2, 3, and in a clockwise and anti-clockwise direction, the numbering will start like 1, 2, 3, 4, 5, 6, 7, 8 kind of thing. If you look at the pins and their significance, let us take pin 1 is ground, means whenever we want to power up this device, we have to provide the power supply. So pin 8, maybe it is coming in the last, we have to start with pin 8. Pin 8 is VCC, where the required power, like any petrol or diesel we are going to give as automobile, we have to give a power supply to make our IC operative. And the counterpart of power supply is ground. So we started with 8 pin and pin 1 ground. Next comes to pin 2. It is trigger. As the name suggests, trigger means like a physical gun or some kind of shooting equipment. So once you have to provide some small initializing pulse, which is known as a trigger pulse. So this is required whenever we want to make the 555 timer output to change from one stable condition to another stable condition. This pin will be used. Pin 3 output. As the name suggests, pin 3, we have to take the output and we need to connect the load, whatever the load we have to connect to the 555. It should be connected between output and one pin number 1 ground. Pin 4 reset. The reset pin functionality is whenever you want to reset the 555 timer, you have to apply some voltage to this pin. While showing the internal diagram, I'll tell you. Control voltage, as the name suggests, it is going to control the complete output of 555 timer. Threshold. So this 6th pin threshold is making your threshold comparator, which is a part of this one. As I have shown you, the upper comparator is a threshold comparator. So the pin connected to this pin is known as threshold. Maybe here we can visualize the pins very properly. And pin 7, it is discharge. As the name suggests, to charge and discharge any capacitor connected to this pin will make its charging and discharge through this transistor and at the pin number 7. And pin 8 is VCC. Once again, I am revisiting all the pin numbers. Let us see. The pin 1 is ground, pin 2 is trigger, pin 3 is output, pin 4 is reset, pin 5 is control, pin 6 is threshold, pin 7 is discharge, pin 8 is VCC. Now we will move on to, this is the physical appearance, this is a pin diagram. All this information, how the pins are located, what are its specifications, we can get it from the data sheet of individual IC from the manufacturer's data sheets. So it can drive maximum of 200 milliamps current, which is connected at the pin number 3 to the ground. Suppose if the output of 555 timer is having high output, then the load connected from pin 3 to ground, we can source the current. But if the situation is reverse, for example, if the 555 timer output is low, then it should be connected between output and a power supply. So then current will sink from the load to the IC. Then it is known as sinking current. So it provides 200 milliamps current, either sourcing or sinking. Once again, the internal diagram, according to the pins, it is exactly connected. You can see pin ground 1 to pin 8, the 3 resistors are connected so that it will produce 2 thresholds, which is known as upper threshold and lower threshold, to start capacitor charge and to take its direction reverse into the discharge. These 3 capacitors and the supplies, the tapping voltages decides whether it should charge or discharge. And these comparators, you can see the trigger comparator, one pin is connected to trigger and another pin is connected to the point, this point. So here the voltage we are going to get will be decided. So at pin number 2, we are providing the voltage from the outside, the trigger, At the other end, we are providing a voltage known as 1/3 VCC, which is tapped from this potential divider network. And for the other comparator, which is known as threshold comparator, one pin is connected to the pin number 6, which is threshold, and another pin is connected to the control, and at the same threshold point, the tapping is available is connected to 2/3 VCC. So this comparator action is whenever the difference voltage is positive, output is producing a high, and whenever the difference is negative, output produced is a low. So like the trigger comparator also. If you look at trigger comparator, one side is connected to 1/3 VCC, another side is connected to trigger number 2. So whenever this comparator output you want to make it high or low, we have to look at the voltages available at pin number 2 and the tapping of 1/3 VCC. So this set and reset will make your flip-flop whether it is high or low. Here we have taken the output at Q bar. Q bar means suppose if set is 1, output of your flip-flop is 1, but its complementary is 0, and 0 is taken through the inverter and it is producing a 0 output. So each and every pin is having its own significance, and whenever we are connecting into a special mode of operation, then we have to connect the external components and see the operation. Basically, this 555 is operated in 3 modes. One is monostable, astable, bistable operations. So these 3 will provide us the basic configuration so that we can generate clock pulses for the operation of sequential circuits, and ability to operate from wide range of supply voltages, and it can trigger and reset the inputs, are logic compatible. Logic compatible means there are 2 types of logics are available. One is TTL logic and another is CMOS logic. So these are compatible means these are directly can drive the loads without having any interfacing circuits. So that is a special attraction of 555 timer. So then we can, these are the specific individual what control voltage, what the reset voltage. Now we'll go back and see once again the reset. What is the reset pin? Now if you look at here, this transistor, whatever I am clicking, one side is connected to V reference voltage, another side is connected to, I am just drawing the line, it is connected to the base of transistor. Suppose if I provide reset pin a positive plus 5 volts, then the difference between base and emitter voltage will be 0. Then your transistor will be off condition. Then this line is disconnected and it operates from the output of flip-flop in a normal mode. Suppose if I connect reset to a 0 voltage, then the VBE between base and emitter will be negative. Then transistor will be on. Then this reference voltage is connected directly to the inverter. So high voltage, and it is making your inverter output 0. That is, when you provide reset pin to 0 voltage, it is making your 555 timer output is 0. Hence, its functionality is, if you don't want to reset the 555 timer, you have to connect this reset pin to 5 volts. Otherwise, if you connect 0 volts, it is going to reset your 555 timer. So that is the reset advantage. Normally, for normal operation, the reset pin is tied up to the VCC directly so that we are having a normal operation based on the inputs we are providing at pin number 7, pin number 2, pin number 6, pin number 5 and so on. There are 3 operations I suggested, 3 modes: monostable, producing a single pulse when it triggered, and it produces a square wave when it is operated in astable multivibrator mode. Lastly, in bistable multivibrator mode, we have to provide some 2 short duration pulses to trigger and to threshold so that we can have this square wave output based on the 2 input signals. That is, it has 2 stable states on and off based on the input trigger pulses which are provided continuously. Then we'll look at the 3 operations in a short and the derivation of what is the output produced from this. So this is a circuit diagram I am showing, which is a stable multivibrator. As you seen, the first I will start with pin number 8. I have provided a VCC. Pin number 4 is a reset pin. I don't want to use, that's why I have connected to a power supply VCC. And pin number 5, it is a control. Suppose if you want to control the timing of your output pulse, then we have to apply externally some control signal. Now, if you don't want to use, this control signal is tied up to ground for normal operation. Then we look at the remaining pins. Here I have tied up trigger and threshold to the same point before starting the operation, and external resistors R1, R2, and for the 6th pin threshold, because inside threshold there is a transistor available. I will show you this connectivity in terms of the internal circuit diagram also. So then we have to make this capacitor to charge to a certain extent by making your internal threshold transistor on and off, so that we can make this capacitor also discharge. So if you look at the charging and discharging diagram of your capacitor, it produces an output like this. So as soon as you power up between 8 pin and first pin, like power supply and ground, it starts producing your oscillations and it never stops. That's why it is also known as free running multivibrator. What is the name? The multivibrator means it has a circuit. A square waveform contains multiple frequency components. If you decompose into Fourier series, that is, any square wave can be decomposed into infinite number of basic sinusoidal waveforms with different amplitudes. So it is a combination of basic component like cos omega naught plus or minus cos n omega naught. These are known as fundamental frequency as well as harmonics. Altogether it is containing various vibrations, like one vibration is at omega naught, second vibration is 2 omega naught, third vibration is 3 omega naught, and so on. It has multiple vibrations with different coefficients, with different Fourier coefficients. So that's why it is containing multiple cosine waves, multiple vibrations. That's why this circuit, which is producing a sine wave which contains multiple vibrations, we call the circuit as a stable multivibrator, and it is also known as free running multivibrator. So this is a simple circuit which produces how the capacitor voltage and then output voltage. Then I am connecting the internal circuit and external components using this circuit. See, RA is connected between VCC and 7th pin, RBC connected at 7th pin, and internally it is connected through this potential divider circuit like this, and it is connected to ground. And RB and capacitor is connected to the pin number 6. Now for a stable operation, I will start as soon as you provide the power supply. The basic voltage at the capacitor is approximately like VCC by 3 initially. So it works on capacitor charging and discharging. We are starting at VCC by 3 initially. You can see the lowest one. So initially VCC by 3, the trigger comparator output at one pin is, the lower pin is at 2/3 VCC, upper pin is at 1/3 VCC. So its output will be low, and the lower comparator, it is 1/3 VCC and output will be high, and reset is high. Q will be 0 and Q bar will be 1, and you are producing 1 voltage, and this is connected, output of internal capacitor is connected to the Q. So basically here Q is 0, here it is 0 because Q bar is 1, it is connected to base of this transistor, and the transistor is in off mode. So initially Q is in off mode. Off mode means this is disconnected from this one and capacitor is charging towards VCC. During this transition, whenever it crosses the next voltage, that is 2/3 VCC, then it is having a change in this component. So this 1/3 VCC is changing to 2/3 VCC, and this low is changed to high. And this output of your flip-flop is going to have set is set is high, that is Q is 1 and Q bar is becoming 0, and output is making a transition from previously high, it is making low. And because of this 0, because of now it is initially 0, now it is 1, transistor is in the on mode. So now Q becomes off to on. Because it is on, so on means the capacitor will discharge like this. So there is a path which is opened for discharging the capacitor. Now the capacitor discharges through this one, and it discharges from 2/3 VCC to again to the back. So now it comes back to 1/3 VCC. Now it repeats, that is previously it is high, now it is becoming low. So these operations of threshold comparator making high low, making your output of 555 high low and so on. So this capacitor is making between two limits, 1/3 VCC and 2/3 VCC. These are known as two thresholds, upper threshold, lower threshold, or threshold and lower threshold we call it as trigger threshold. So this is the equations. The equation of capacitance, I have taken capacitor across capacitor voltage, which is taken as V final plus V initial minus V final into e power minus TRC. So there are two components. At T1, which is charging, initially voltage is 1/3 VCC and it should reach finally VCC. At the end of T1, the capacitance voltage is 2/3 VCC. If I substitute in this one, I am getting the charging time as 0.69 RA plus RB into C. And similarly, from the 2/3 VCC where it has achieved, so then it should drop down to 2/3 VCC to 1/3 VCC at the end of discharge time. That is, we have to take the discharge equation. V capacitor is V initial into e power minus t by RC. At time t is equal to T2, it discharges from initial 2/3 VCC to 1/3 VCC. You substitute these values, I can get the discharge time as 0.69 RB into C. Now the total time is charging time plus discharging time. This is 0.69 RA plus 2 RB into C. If you take inversion of time period, we can get the frequency 1.443 by RA plus 2 RB into C. It has another parameter known as duty cycle. How much time it is in the on mode, that is the output is taken as high. So it is known as T on plus divided by T on plus T off into 100%. So if you substitute these values in the above equations, the duty cycle is RA plus RB by RA plus 2 RB into 100%. That is how much time it should be in on, it should be off mode. We can control by using the resistors RA and RB. This is T on, this is the T off. So any clock pulse you are producing, you can have our own on time or off time. It can be controlled by controlling the resistors RA plus RB divided by RA plus 2 RB. Then if you want to make both on time and off time equal, then I have to connect two diodes here and making the charging through this diode and discharging through this diode, so that we can maintain the total resistors together R1, R2 and together R2 and diode across resistance, diode resistance across diode. These two we can manage in the circuit so that your duty cycle should be equal to 50%. That is exact square wave clock pulse if we require, then this is a special arrangement we have to make. Then we'll come to the monostable second one. Already we have seen the internal diagram. So we can remember what is 672. So I am connecting pin number 2 is connected through a switch and a negative trigger pulse. So this is going to one part of one of the inputs of trigger comparator, that is down, and 6th 7 is tied up to the center of this R1 and C1. So initially we are assuming the voltage at this position is approximately VCC by 2, and upper comparator, lower comparator positions are such that it is producing whatever the state is previously assuming. Just I am showing once again here. So this voltage is VCC by 2, this voltage is also VCC by 2. So both are in lower conditions now. So just I'll make this one. So now here it is, both are in low and condition. Both are in low, so output is in previous state. Whatever the state it is assuming, why this is low? Because it is both are VCC by 2 and another one is VCC by 3. So here also one side is connected because it is left open. The pin number 2 is taking VCC and here it is 1/3 VCC. So if you look at the conditions of the comparator, the output of your SR flip-flop will be in the previous state. So whatever the state we are assuming, whether it is low or high, it remains in the same state. Now coming to the circuit, if you apply a negative trigger pulse, which is an amplitude of 1/3 VCC. So why we are providing 1/3 VCC? If you provide here 1/3 VCC at this trigger pulse, 1/3 VCC, then this comparator output we are making high, that is reset is high, then Q will be 0, Q bar will be 1. So previously we are assuming that, so because it is 1, it is 0, we are making your transistor to switch off. Now we are allowing the capacitor to charge. So to allow the capacitor to charge, this one, so we are providing a trigger pulse at pin number 2 and making capacitor to charge through resistor R1. So this R2 is for this one. Actually this is the path. So it charges like this. Then it charges until whenever it crosses 2/3 VCC. Then your upper comparator so will come into the action. So whenever it crosses 2/3 VCC, it is making its transition into high and output is 1, making your discharge transistor on. Now previously it is off, now it is making into on. So now capacitor is connected through this transistor and make the discharge. So now we'll come back. So at this, whenever it is crossing 2/3 VCC, it is coming back. So this pulse width, how much time it should be in the on condition? So initially it is low. Now we are applying a trigger, something like pushing a trigger for your gun kind of thing. So it releases one output and then it comes back. It comes back to the normal state. So it is producing for every trigger pulse one standard stable output. And it is only initial voltage, we are starting the charging pulse and then at the end of the capacitor, at the end of the time period, it reaches 2/3 VCC. We started with initially VCC. Then if you apply in this one, we are going to get what is the pulse width, amount of time it is retained at that pulse. It is decided by a component R and C. It is 1.1 times RC. Basically, it is used to trigger some other circuits like a stable multivibrator or any other device which you want to have your on and off of that particular circuit at our user control. So user uses this trigger pulse. Maybe this can be used as some kind of alarming signal when you are trying to build an application like burglar alarms or theft alarms or some alarm detectors, fire detectors. So this can be used as a trigger pulse so that whenever it triggers, it gives out a pulse which is used as a warning pulse. So that's why monostable multivibrator and a combination of a stable multivibrator, we can generate lot of signals like special signals which can be used for ambulances or any other special warning purposes. We can use this monostable combination with a stable multivibrator. And the last version of 555 is, it is a bistable multivibrator. So here we are using a continuous input sine wave, and as you see, in each and everywhere we have two limits for your capacitor to charge, lower limit and upper limit. Lower limit is always 1/3 VCC, upper limit is always 2/3 VCC. So the type of input signal to make your output low to high, we are taking or extracting the two threshold points, upper threshold point and lower threshold point from your input signal. So initially, if you look at this operation, initially it is at VCC by 2, the basic point at this one. and internal comparators inputs and outputs. So initially, suppose it is in the high condition, that is, if you look at again here, we are connecting internal one, all are connected together. So initially it is at VCC by 2. This trigger threshold comparator, what it is functioning, it is low and output is 0 and output is 1, and 1 is taken through a inverter, then output will be so initially it is VCC by 2, it is low. Low means output is 0, and if you take through a converter, it is making a output as 1. Okay. Then whenever it is crossing 2/3 VCC, upper threshold is making a high, and output of your reset RS flip-flop is made as 0, and if it is taken through an inverter, it is making a transition to 0. And whenever it is making less than 1/3 VCC, trigger comparator is triggering, then the lower comparator is making reset as high. So reset high means output Q bar will be 0 and it is 1. Okay, so output is making from 0 to 1 transitions. So whatever the capacitor charging and discharging threshold points, UTP and LTP, we have derived from a input source. And whenever it is crossing upper threshold, it is making a transition from high to low. Whenever it is crossing lower threshold, it is making a transition from low to high. So in this way, a sine wave is converted into a square wave. So this is also known as sine wave to square wave converter, or as from the scientist, it has invented the name which is known as the scientist Schmidt. It is called a Schmidt trigger, because it is taken a input pulse, which is also known as a trigger pulse, and it is converting. This trigger may be anything, a sine wave or a triangular wave or any wave, or even a irregular having a noisy wave. So it will not consider any noise, only it looks for the threshold points and it makes the transition. So maybe it can be converted a noisy square wave into a clean square wave, or a noisy wave into a clean wave. So this can be used for a converting any noisy pulse into Schmidt trigger, or it can produce two stable states. So this is one stable state on, this is another stable state off. So this produces two different stable states. So basically this can be used for converting any noisy pulses into a clean pulses. This is the basic application of bistable multivibrator. So we have discussed three multivibrators based on 555 and few basic components like two resistors, or sometimes two resistors with one capacitor, and this capacitor which is connected at the input, which is meant for just cleaning any DC signal which is available in the input signal. To block DC or to filter the DC, this capacitor will be used. Wherever the capacitors we are using in the circuit, so they are just to clean up the signals or any noise pulses which is very high in nature. So they are going to be passed onto the ground. So that is a safety measurement. So whatever we are using, so for the safety measurement. So this is for the three different pulses, three different multivibrators we are using. So basically this linear integrated circuits, more or less the components we can get it from the textbook Linear Integrated Circuits by Mr. Roy and Chowdhury. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.